I'm thinking that the exam will cover part of chapter 0.5. It's a short chapter and it's really just a rehash of chapter 0, but in terms of electric fields, not gravitational fields. I'm also expecting that the exam will have a take-home. Hopefully we'll get to that today, and you'll be able to do that. It's going to be largely a derivation that you can probably find online or you can do on your own, but I just want you to put your pencil to the paper for it, and so we'll have that as a take-home. We'll do some of it in class, but then the rest of it you'll have to do outside of class. So we started on electric fields, and remember we defined the electric field last time. I talked about we have forces, fields, and then later we'll get to potential. So forces are defined by Coulomb's law. Electric fields are really just a way to describe the force. In fact, sometimes we call these force fields. I think that your Latin instructor, not me, but the better looking one, that she describes them as lines of force or as force fields. I usually don't use that terminology, but it's a good way to think about it, that it's describing the force. And then, so in a similar way, if gravitational fields describe a gravitational force, electric fields describe an electric force. So we have forces, fields, which are a force per unit charge, and then later we'll get into potential after this exam, which will be energy per charge. So you can think of it in that progression: forces, fields, and potential. We defined electric field last time as a force per unit charge. This is the definition of electric field. It's just something we sort of made up to help describe forces. And Coulomb's law, if we imagine that we have a charge Q and a charge Q naught, or we sort of introduced this idea of Q naught, which is a test charge, an imaginary positive test charge, then we can use Coulomb's law to describe the force. So that force between those two charges is K, Q, Q naught over R squared. And then combining this with the definition of the electric field is force divided by this imaginary test charge. We're going to use our imaginary test charge to sort of trace out the field. So for example, if I have this charge right here, I have my imaginary test charge, and that imaginary test charge tells me that the electric field is in that direction, and that the force that this charge experiences is related to the field. All right? Imaginary test charge is just a tool that we use to map out the direction and the magnitude of that electric field. You're with me on that? Sometimes that's difficult for people to conceive of. But we notice that the electric field is not dependent upon the test charge, because look, if I take this one step further and I put in my Coulomb's law, and then this is all divided by Q naught, we get this expression for the electric field that is KQ over R squared. This is on your equation sheet, so no need to memorize it. But do note that it looks very similar in form to Coulomb's law, and for good reason, because, it's based on Coulomb's law. In fact, Coulomb's law is our fundamental idea, and then we'll extend it to fields, and then we'll extend it later to potential. But we're always going back to this basic idea of the force between two charges. Just like we did with going back to the force between two masses, Newton's universal law of gravitation, that this is sort of the underlying idea behind all these things. So the E field is not dependent upon the test charge. That whether we have the test charge or not, the electric field is there, right? We just use that test charge to map out the test charge. And the test charge is merely a tool, is only a tool. Oh, I'm sorry, the test charge is only a tool to measure or sample the electric field. Field. Somebody criticized my spelling on the exam. I'll find out who you are. I forget who it was, but I will find out. I misspelled a word. Okay, so the electric field is a tool. It's not really a tool. It's really just sort of a thought tool, like a thought thing that we think about, because we don't actually have a test charge. We're just using it to sort of think about what the electric field is doing. The sign of the charge determines the direction of the electric field, and the direction of the electric field is the same direction of a force that the positive test charge feels. That positive test charge, that's that plus Q naught. So imagine here, if I have a positive test charge next to a negative test charge, it feels an attractive or repulsive force. It's attractive, right? Like opposite charges attract. So if this is positive, it's going to feel a force in this direction. And so similarly, the electric field at that point is going to be in that direction. So I can draw it as a vector. I can draw it as a long line describing if I move this positive test charge along, the electric field will always be in that direction, attractive. And similarly over here, if I have a positive test charge, it's going to feel a repulsive force. So the force here is in that direction. The electric field, sorry I switched colors on you, but the electric field is in that direction. I use my positive test charge to figure out what's the direction of the electric field. And the electric field goes into negative charges and it comes out of positive charges. We had this with gravitational fields too, except with gravitational fields, because they always experience attractive forces, those fields always go into the mass. They never come out of the mass. Okay? All right, so we can use the superposition principle. One more time with vectors. You will have a vector problem on the test. You had one on your pre-test. It'll either be charges, it'll be electric force, or electric forces, gravitational forces, or electric fields. But we'll also have some multiple choice questions that ask you about these vector problems, and particularly with fields. So we can use the superposition principle to find the electric field. So say that we want to know the electric field at some point right here. We imagine that we put our positive test charge at that point, and then we figure out what is the direction of the electric field to these individual charges. So at this point, where I imagine I have my positive test charge, I ask myself the question, what is the electric field due to Q1? This charge feels a force, feels two forces in fact. Due to Q1, it feels a force in this direction, I'll call that F1. And due to Q2, it feels a force in that direction. I'll call that F2. And so remember, electric fields and forces, they're in the same direction. In fact, they're related to one another. And so I can draw now my electric field vectors. I have E2. That's the electric field due to this charge. And then I have E1. That's the electric field due to this charge. Electric fields and forces. An electric field is just a force per unit. Force per unit what? Electric field? Charge, right. So similar to gravitational fields, that was a force per unit mass. But here we're talking about a force per unit charge. And so the net electric field is just a vector sum of these. If I want to know the net electric field at this point, I do the sum of the electric fields. That's going to be E1 minus E2. Just do the vector sum. And so if the charges are identical and we are the equidistant between the two, then what's the electric field going to be? It'll be 0. So if the charges are identical, the electric field will be 0. Remember, that's in newtons per coulomb, or sometimes we see electric field also in volts per meter. All right, let's do a 2D problem. It's our third time to do it, but I want you to make sure you get these vectors. So what I want to do here is figure out the electric field, just sketch it in. Due to this charge, it would feel an attractive force, a positive test charge at that point. So my electric field is in that direction due to this charge. Attractive or repulsive? I have a positive charge here. I imagine a positive test charge here. Is it going to be down in this direction, or is it going to be up in that direction? Quadrant 1 or 3? It'll be in quadrant 1, right. So those are the first questions that you ask yourself. Sketch in your electric field vectors. Then we also want to know what is this angle, recognizing that we have a triangle here. It's a 3, 4, 5 triangle, so that distance is 5 meters. And if you know your 3, 4, 5 triangle, this angle is 37 degrees. If you don't, you do the inverse tan of 3 over 4. And that'll give you 37 degrees. Okay? So I now calculate the magnitudes of E1 and E2. E1 is KQ over R squared. That's 9 times 10 to the 9th. That's our K value. Q is Q1. That's 3 nanocoulombs, or 3 times 10 to the minus 9 coulombs, divided by the distance to Q1, which is 5 meters squared. These cancel, so I'm left with 27 over 25. That's in newtons per coulomb. And then I do the same for E2. 9 times 10 to the 9th. 2 times 10 to the minus 9. Remember those micro and nano prefixes, please. Divided by 4 squared. Those cancel. It's 18 over 16 newtons per coulomb. All right, both of those are just a little more than 1 newton per coulomb. Now that we know that, we know the magnitudes, now we find the components of E1. I set up a new coordinate system. You might not draw all these pictures, but I find it useful to do so. E1 has two components. The first one's going to be 27 over 25. That's its magnitude times the sine of 37. And 27 over 25 cosine of 37. And then E2 had a value of 18 over 16. Now we figure out what those are. So I have 0.65 0.86, and this is equal to 1.1. We'll just call it 1.1. All right, I add up my x vectors. I only have one vector. The sum of this and this are going to put it in the negative x direction. We're almost there. That sum over here is going to be 1.1 minus 0.86, so that's what? 0.24 newtons per coulomb, 0.65 newtons per coulomb. And then I find the resultant of that. The resultant vector will lie in that second quadrant. I want to know what this angle is. I'll call it phi. And I want to know the magnitude of that vector. You could express it in vector notation, but on the test I want to know the magnitude and direction. So the electric field vector is 0.24i plus 0.65j. But the magnitude of that electric field, and some of you did that, by the way, for the pre-exam. That's okay. I should have been more clear. I really want to know the magnitude and direction. 0.24 squared plus 0.65 squared. That's 0.69. So that's my magnitude. And then I also want to know the angle. Phi is the inverse tan of the y component, that's 0.65 divided by 0.24. I get 70 degrees. Does that seem reasonable? Yeah, that seems reasonable, because my y component is a lot bigger than my x component, so it's going to make that vector go, you know, on the high angle. And that's 70 degrees above the negative x-axis. Alrighty? Many of you couldn't do the problem on the exam, so make sure that you can do that, the one with the 3 masses, because it'll be something similar to that. Why? Oh, good question. So y is 0.24 positive. Oh yeah, so right here where I have it in vector notation, is that what you mean? Yeah, it should be negative, thank you. It doesn't matter here because it's squared anyway. And actually with the tangent, I'm measuring this angle, so I keep it as a positive. Some of your calculators are smarter than others, and you know, if you put in a negative x component, it'll get the angle right. But some of your calculators don't get that right. They'll measure it in another quadrant. So I recommend you just strip those signs off for measuring the angles. All right. These are your last jab at vectors for this class. You engineering majors especially, you have whole classes that are centered around vector analysis, and Calc 3 too. I think you'll do some vector math. Y'all do vectors in Calc 3? Anybody been in Calc 3 yet? Yeah. Like more vector addition like this, as well as multiplication, cross products, dot products. Oh yeah. All right. All right. Let's try this little quick test. You might have some questions like this too on the exam, which is coming up on Monday. While y'all are doing this, I'm going to hand out those that came in a little late. Again, this is not for grade. It's out of 41 points. So just add up points to this. Divided by 41. On this, you want to sketch out your vectors, your electric field vectors, and ask yourself the question, where is it going to be bigger, A or B, or were they of the same magnitude? Think about the distance that you are from the vector, from the charge, and then also think about the magnitude of the charge. Remember, electric field is kq over r squared. That's the electric field due to a point charge. We're going to do objects next. Right now, you're pretty evenly split on the answers. All right, we'll do about 7 more seconds. I'm going to stop at 150. 150. Awesome. Okay, yeah, we're sort of split. Make sure that you're good on these types of questions, because you'll certainly see them. But it also helps you in the free response part, because it helps you to think about how to draw those electric field vectors. So at point A, I want to think about the contribution of these individual charges to the electric field. Now, at point A, I imagine I have a positive test charge, and I ask myself the direction, or I ask myself the question, what is the direction of the force due to this charge? Left or right due to that charge? Right, it's a repulsive force, and so that force, as well as that electric field, will be to the right and in that direction. Okay, let me make it a little bit bigger. I also want to try to get my relative sizes of the vectors correct. Now, the minus 4q charge will be to the left or right. It's an attractive force, so if I imagine a positive charge here, it will be attracted that means the force is in this direction, and so is the electric field. All right? How much bigger or smaller is the electric field due to this charge going to be than this charge? First of all, is it going to be a bigger electric field or a smaller electric field than the blue one I've drawn? It's going to be bigger, right. And by what amount is it going to be bigger? It's going to be twice as big. The charge is twice as big, and the distance is what? It's the same. Okay? So if I double this charge right here, keep this the same, I double the electric field. So if I draw my electric field vector here, it's going to look like this. It's going to be twice as long. Now let's think about the other side. The answer, by the way, is A, so let's go ahead and do that. Think about the other side, doing the red first. Left or right on that one? Attractive or repulsive? Attractive, which is left or right at point B, is to the left, right? So the electric field is to the left, and it's going to be actually the same length as this vector. Now let's think about the electric field over at point B due to this charge. If I have a positive charge over there, attractive or repulsive to this charge? Repulsive, right. They will tend to go apart from one another. So my field is to the right. Is it bigger or smaller than it was here? Smaller. It's smaller. And do y'all know by what amount it's smaller? Think about it for just a second. Don't say it right out. All right. By what amount is the electric field smaller at point B than it was at point A? So when I draw this blue vector right here, by how much smaller is it going to be than this vector? Good test question, okay? Thinking about how does changing the distance affect the electric field? Ask yourself the question, by how much more or less is this distance than this distance? The distance between the plus 2q and B is how much bigger than the distance from the, than this distance? It's not half. They're not equal either. There's not 4. All right, look, you can think about it, divide it into sections of 3. 1, 2, 3. This distance from here, let's see what am I doing here. This distance from here to here is one of those segments of 3. The distance from here all the way over to here is 3 times that distance. Y'all follow me? Let me draw it. I'm not sure that y'all are following. I'm thinking about 2 different distances. I'm thinking about this distance, and I'm thinking about this distance. And notice that this distance has 1, 2, 3 segments that are all the same length. So I've increased my distance by a factor of 3. That means my electric field is going to be decreased by what amount? Not a third. Yes. A ninth. Because it's r squared. If I increase this by 3, I decrease this by 9. All right? We'll see some more questions like that. But if I draw my vector, I draw itty bitty, 1/9. It's 1/9 the size of the original vector. That's over at point A. All right, so if you think about how those vectors are arranged, point A has the bigger electric field. Okay, we'll come back to that. We'll see some more questions about that. But let's now move on to regularly shaped objects. This is going to be a take-home, and I'm going to do the first one for you, and I'm going to leave the other 2 for you to look at, and then I'm going to give you another one to do for the take-home. And I'll send it out no later than Wednesday, but I'll try to get it out tomorrow or no later than tomorrow. But give me till Wednesday at least. I'll probably give you a cylinder to integrate over. It's really just dealing with volume intervals. We've done this before. We did it last semester when we did, moments of inertia. Remember doing that? We did the cylinders and the spheres and all that jazz. It's a useful tool to be able to integrate over three variables, to integrate over volumes. And it's kind of fun. Like, don't you agree? Like, doing these volume intervals is kind of fun. I remember in college, that was like the most fun that I had in calculus. volume integrals. Do you agree? Y'all haven't had volume integrals yet, because you haven't been in Calc 3 yet. But when you get there, you will agree with me that it is the most fun. You look excited. All right. And for you engineers especially, and for you chemists, you go on to grad school, you'll see it there as well as you think about, you know, different molecules and how their charges are arranged, and in other practices. This is the basic idea of it. Let's consider a ring, because a ring's really easy to think about the electric field. If I have a point here, I divide my ring into little bitty pieces. I have a ring of charge where they're all evenly distributed around the ring. These are our differential elements. They're dq, right? You'll talk about differential elements in your calc class. Yes? Y'all call it something else or no? Differential elements. You know what I'm talking about? No, it's not a differential equation. It's like when I think of dx dt, or when I think of the integral of x with respect to time, that's our differential element. That I'm taking a physical thing and I'm breaking it up into a bunch of little pieces. In fact, you break it into an infinite number of pieces. Okay? So that's physically what you're doing when you're doing an integral or a derivative, that you let these things, you break your, whatever your measurement is, into little bitty pieces, and you let the size of those little bitty pieces get really, really, really small so that you have an infinite number of these little pieces. And then in this case, we're going to do an integral because we're going to ask ourselves, what does the electric field do to each of these little pieces? And so the electric field here is in that direction. The electric field here is in that direction. The electric field due to this little piece is in that direction, and on around the circle. You know, also thinking about what's the electric field do to all these little elements as I go around. And I do a summation. That's our integral, right? It is a summation when you look at the definition of an integral. And I add up all those little pieces. And in this case, I get vectors that look like this. And so you can probably look at that and tell me what is the net electric field at the center of that ring. It's going to be 0 because all those vectors are equal and opposite, and they're all going in different directions. Now, if I had my point over here, it wouldn't be so simple. But you can imagine that if our point was over here, that you could break these things into differential elements, and the strength of the electric field would vary based upon where you are on the circle. And then you have to set up an equation in some way relating the distance from the ring to where you are on that circle. And that's sort of what we're going to do in these first examples. But in that case, at the red point, your electric field would not be 0 because your vectors would not be all equal and opposite. All right, so the center of the ring, electric field is 0. All right, so let's look at 3 configurations, but actually we're probably only going to do 1, and then I'm going to leave you to look at the other 2. They're in your homework, and I'll send you the one that you'll do for your take-home exam. It'll be worth, 10 points. If you look around on the internet, you can probably find the answer. You can work together. I expect everybody to get it, so if you put some time into it, you'll get that 10 points for sure. Okay? I just want you to be exposed to it. So when given a continuous line of charge, one can integrate over the shape. Divide the object into differential elements. Or, we'll call these itty bitty pieces. Because that's really what they are when we're talking about, a physical object. We imagine that we break it up into little bitty pieces that are infinitesimally small, very, very small, and then we integrate to find the total electric field. integrate all those little bitty pieces and how they contribute to the electric field to find the total electric field. And so we're going to consider three configurations of charges. The electric dipole, and this one is actually going to be quite a bit different from the other two, which is why we're going to do it here. But it's important. You're not going to see the electric dipole on the exam, or henceforth you won't see it. But it's an important charge configuration because electric dipoles occur a lot in nature. And so you chemists especially will likely see the electric dipole later and how those two charges react to one another and the electric field that they create. But we'll also look at the charged ring and the charged disk. And probably what you'll have on your take-home exam is a cylinder, but I'm not sure about that. I have to take a look and see. Maybe. All right. It's also useful to define a charge density when we're looking at these. So charge, just like a distinct charge that we have, we use Q, just like we've seen already, and the units are in coulombs. But kind of like what we did last semester when we did moments of inertia. I think we use like a linear mass density and an area mass density and a volume mass density. We'll need similar things for this. So let's just define what those are. We have a linear charge density. We usually use lambda to describe that. I don't know, lambda like a line, if you want to think of it. L, that's the Greek letter that we usually use for L. And this is in coulombs per meter. So, if we had a line of charge and we had a bunch of little charges, we would ask ourselves, how many charges do we have per unit meter? That's our linear charge density. We use it for mass density. We use linear density quite a bit, actually. Anytime I have something that's extended over a line, then I can use linear densities. We can also have an area, or surface charge density. So if I have charges over an area in 2 dimensions, then I can use this. This came up in your little pre-exam too, when I asked you to derive the gravitational field on a flat sheet of mass. So like if you were looking at the universe, a big flat structure out in the universe, then you might use that to describe the gravitational field. And I asked you to describe it in terms of sigma, which was the mass, the surface mass density. But we can do the same with charge. And so we use sigma, and this is coulombs per square meter. And then finally, the one that we're all familiar with is the volume charge density. This is rho, Greek letter rho, and this is coulombs per cubic meter. That's the one we use most often, but sometimes these other two are more useful to use because you have material that is a quantity, be it mass or charge or whatever it is you're dealing with, that's spread out over a line or out over an area that's in 2 dimensions, over 1 dimension or 2 dimensions. Okay, y'all with me? What we're getting up to is we're going to take an object and we're going to break it into discrete pieces, differential elements, and then we'll integrate over those pieces, or we'll just add them up, doing an interval, and then we'll express the result in terms of these charge densities. Actually, the first one's a little bit different from that, so let's jump on into that one, the dipole. These are in your homework too, by the way, so the solutions are on the homework solutions page. Here's a dipole. I want to express the electric field at a particular point, at a point that's up above the dipole. The dipole exists of 2 equal but opposite charges, so positive charge and a negative charge. It actually occurs a lot in nature when we get these 2 charges. You can also get 2 positive charges that are somehow connected to one another, like so anyway, you can have these dipoles that occur in nature quite a bit. Our electric field is going to equal to the electric field due to the positive particle minus the electric field due to the negative particle. So if I think about this, the electric field due to the positive particle is in this direction, and the electric field due to the negative particle, which is going to be actually quite a bit smaller, will be in that direction. It's smaller because it's what? It's farther away. So this is going to be KQ over R. I'm going to call this R plus squared minus KQ over R minus squared. And if I describe this in terms of Z, because I want it in terms of Q, D, and Z, it's going to be KQ over Z minus 1/2 D squared minus KQ over Z plus 1/2 D squared. See, I just took this distance from here to here, and I said Z minus half the distance, because the point P is the same as this distance. We're just expressing these distances R in terms of Z and D, because those are our physical measurements. The Z, the distance up to the point where we are, and then D. I can factor out a 1 over Z squared from the denominator. This is a little tricky. It's going to look something like this. If I have 1 over Z minus 1/2 D squared, that's equivalent to 1 over Z squared times 1 plus D over 2Z squared. I'm not going to go through sort of how that happens. You can go through the algebra later if you want. But I can factor out this Z squared from the denominator. This business is equal to this business. All right? And also, please note, my Z's have lines, my 2's do not. So they will look similar otherwise. Now I can rewrite it. I get E is equal to KQ over Z squared times 1 minus D over 2Z to the negative 2 minus 1 plus D over 2Z to the negative 2. All right? Listen, I don't want you to sweat this too much because I'm not going to test you on the dipole, but I just want you to see sort of the process that we go through, because you might see it again later as you get in, probably not classes here, although you might see it in PTEM, but in going into graduate school you might see this. So I don't want you to sweat this too much, but it's just sort of the process that we go through, the mathematical process to develop an expression for the electric field. It comes up elsewhere. All right, so I can make some assumptions. I can say that when Z is much, much bigger than D, that is, if I'm really far away from this dipole, then D over 2Z is much less than 1. Right? If I make this denominator really big and this smaller, then this becomes much less than 1. So I can use because of that, I can use the binomial theorem. You've probably seen this in calculus. You might have used the binomial theorem. It says that 1 plus x to the n is equal to 1 plus nx over 1 factorial plus n minus 1 x cubed over 2 factorial plus and on and on. All right, I'm just going to use the first two terms. The binomial theorem, I can just replace terms that look like this with this, what's that called, a series or something? What's it called when you have that? Y'all know? I'm not sure. All right, so I can replace a function that looks like this with an expansion that looks like that. I'm going to do so. So I get, well, I'm going to skip ahead and sort of skip that substitution because I'm not going to test you on it. And what we do is we get an expression that looks like this. KQ over Z squared times 2D over Z. And that's equal to KQD, excuse me, divided by Z cubed. All right, so that's the expression for an electric field due to a dipole when I'm looking at some point above that dipole. Again, you're not responsible for this. So if you want to write a note, say, you know, don't study this for the test. But I just want you to see the process that you go through because you might see these derivations similar to this later, where you use things like the binomial theorem and you rewrite these terms in these different ways to help you derive expressions for that. Alrighty? Now, the next part, I'm going to sort of get you started a little bit on it, but then I'm going to leave you to look at it in your homework. But let's say that I have a ring of charge. I have some physical object that's a ring, and I want to know the electric field up at some point Z. What I'm going to do is I'll break it into differential elements. So these little pieces, I say that they have a length ds, and then I describe the various things that I have. So I have the distance here, which is Z. This is the radius of the ring. I can define my angle there, and then little r is the distance from the point to the ring. So those are all of our various definitions for what we have, and I want to express this, the electric field, in terms of Q, Z, and R, because those are my physical dimensions. Q is the charge, the total charge on the ring, but we'll express it in terms of linear charge density. Z is the distance up here, and then R is the radius of the ring. Actually, I don't know, do you want to go through this, or we can do some clicker questions? Why don't we do some clicker questions now, and we might come back to this on Wednesday, but let's do some clicker questions now. We didn't finish this one, did we, the chapter 1? Did we finish this one? You finished it completely? Will I verify that? Is that, did y'all write down the one we stopped at? Huh? 1.3a? All right. We did not do this one? Okay. All right. What is the magnitude of the force F2? So that's F1 here. What is F2 equal to? All right, let's stop at 30. Stop at 30. We'll go on to 32. There we go. Okay, good. It's 3 newtons. Coulomb's law says that, or Newton's third law, rather, applies here that if we have a force in one direction, we have a force that's equal and opposite in the other direction. So if I have 3 newtons here, I also have 3 newtons here. And then it's also, remember our Coulomb's law, F is KQQ over R squared. So notice that I have both charges in this expression. If I change one of the charges, it changes the force on both of the charges. Think of that as Newton's third law. If we increase one charge to 4Q, what is the magnitude of F1? So initially F1 is 3 newtons. But what if I increase one of the charges, this one, to 4 times its original value? What then will be the force? All right, we're going to stop at, say, 20, or excuse me, 42. 42. Just guess if you're not sure. Okay, good. C is right. That if I increase one of the charges by a factor of 4, it increases the force by a factor of 4. And what do you call a guy with a car on his head? Jack. All right. That's also Coulomb's law. What happens if you increase the distance between the charges by a factor of 3? Here, the force on these charges is F. What is it on these charges? They're going to have the same force, but what is the force going to be? The new magnitude of the force. I mean, the two charges will have the same force, but how will it differ from the force on the previous two charges? All right, we'll stop at 33. 33. Is it the same person that waits until the very last minute? It is? Okay. It's okay. All right, good. E is right. It's a 1/9. Is that KQQ over R squared? And so if I increase R by a factor of 3, then I decrease F by a factor of 9. We're also going to see that that's the case for electric fields too, because we have this inverse square law. We had it for gravitational fields and gravitational forces as well. In these two charges, is it possible to place a charge in between these two charges so that the force on that charge Q0, this test charge, if you will, it will be 0? Well, the force, can I place a charge somewhere between here so that the force on it is 0? All right, we'll stop at 52. 52. Okay, we're sort of... All right, let's see. So B and C. All right, let's see. If we put a negative charge here, think negative Q, the force due to this charge will be in this direction, and the force due to this charge will be in that direction. They'll have attractive forces. So if it's negative, there is a place that we can put it so that it will be 0. By the way, will I put it closer to this charge, closer to this charge, or in the middle? To the left, right, or center? Where are we going to put it? To the left, right. You want to get it far away from that big charge because the big charge imparts a greater force. So I want it to the left. But imagine, too, that if I had a positive charge here, you can't really see that, can you? If this was a positive charge, that I would have similar forces, that I would have one to the left and one to the right. And so in a similar way, I can put a positive charge there as well. It's just the two forces are going to flip. All right, so it is C here is the right answer. I would expect some questions like that on the test where you have to think about where you can put charges such that they have an electric field or a force that would come out to be 0. Proton and neutron are a distance of 1 meter and then released. As they approach, what happens to the force between them? Proton and electron. All right, let's go to 32. 32. Okay, good. The force does get bigger because remember, that force is kqq over r squared. And so if I let r get small, and that's what's happening here, is they're getting closer together. As this gets small, this gets big, precipitously big. Like it gets big really fast because it's that 1 over r squared dependence. What particle has the larger acceleration? The proton, the electron, or do they have the same acceleration? They have the same force. We know that to be the case because, you know, third law and all that. But which one has the bigger acceleration at any moment? All right, let's stop at 28. 28. 30. 30. All right. Do y'all know which is bigger, a proton or electron? Proton's a lot bigger than an electron. It's like 10,000 times bigger almost than an electron. It's just a lot more massive particle. It's 10 to the minus 31 kilograms for an electron, 10 to the minus 27 kilograms for a proton. So while you might not think it's very big, it's actually quite a lot bigger. And because it's a lot bigger, the smaller those particles, you know, F equals ma. If m is really small, a is really big. And so the electron will accelerate at a much faster rate, 10,000 times the acceleration of the proton.
I think you picked C as the right answer.
Did I? Thank you, Bernard. All right. Where would they meet? Same situation. Where would these two particles meet? And then we'll make this the last one. But I have a good joke for you, so don't leave just yet. We'll stop at 22. 22. Oh, that's not quite 90%. Listen, the proton moves really slowly. The electron zooms over, so it meets closer to the proton. And what's the difference between roast beef and pea soup? This is a middle school joke, okay? So just watch out. The difference between roast beef and pea soup is that anybody can roast beef. But you can't pea soup, not anybody. All right, y'all have a great day. I'll see you Wednesday. Oh, let's see. Everybody get their pre-exam? If you didn't get it, Kat, Tamara? No.